Hello and welcome back. In my last video, I reviewed this isolation transformer and found a problem. Sometimes when switching it on, it would trip the power. That's caused by something called inrush current, and it can be unpredictable. So in this video, I designed and built a soft start circuit to fix it. I'll show you how it works, how I built it, and how well it solves the issue. So let me tell you a little bit more about what causes this inrush current. When a transformer is switched on, it doesn't immediately behave normally. It first has to build up a magnetic field, what we call a magnetizing flux. The problem is, how that flux builds up depends on when in the AC cycle you switch it on. If you happen to switch it on at an unlucky moment, like near a zero crossing, the flux can overshoot. And when that happens, the core can go into saturation. When the core saturates, the transformer loses its inductive reactance to current. So now, the only thing that's limiting the current is the small resistance of the copper windings. That's what causes the large inrush current, even with no load connected. And it gets worse. If there's leftover magnetism from the last time it was switched off, the core starts closer to saturation. So the next time you power it on, it can hit saturation even faster, leading to an even bigger surge. This video went a bit long, so I may do a part 2 that details the schematic design of the soft start circuit, so look out for that video next. I have included a clip from the isolation transformer review video illustrating the power tripping behavior. Sometimes when I switch on the isolation transformer, it's fine, and then sometimes it trips the power. This is the board layout which I am looking at doing for my capacitor dropper circuit. This is just a rough layout, what it might look like. All these parts are actually recycled, except for maybe 3. This little fuse, which is 250 milliamp, this transistor, and this Zener diode. The rest are all recycled parts. Now, before I actually assemble all of this and do all the soldering, I thought it would be a good idea to actually test the hypothesis that this thermistor is going to stop my isolation transformer from tripping the power by putting it in series with the power line. The idea is that this will initially have a high resistance, prevent some of the surging current, and once it heats up, it will drop its resistance, and then things will just work as per normal. But rather than leave it in the circuit, I have put all this rest of the circuit with a relay to actually short circuit this out so it doesn't actually heat up and get too hot. And also because thermistors, when they do get hot, they can take a minute to actually cool down before they work again as their function, having high resistance at the beginning. And if I want to power cycle quickly, I don't want to have to wait for this thing to cool down. So by short-circuiting it out of the circuit, it won't get hot. It'll just be bypassed, and the relay will take most of the current. Okay, so that's the plan. So I'm going to wire these things up, and just these two first. I'm going to remove everything. I'm going to probably drill some holes here so I can screw it in. I've actually found this power socket board, or box, and the board is going to sit in here, upside down, and I might cover it, and then this will be housed inside the isolation transformer. The key thing to remember, this capacitor dropper circuit is actually a very dangerous circuit to use because it's actually floating at mains voltage. Even though this thing eventually will be putting out 12 volts to power the relay, the 12 volts is relative to the mains. And because it's not grounded or have a ground reference per se, if you touch it in certain places, you can still get a bad electric shock. hence the housing inside the box, which I also need to confirm that it actually can fit inside the isolation transformer, which I believe it does. So let's get to the next step and do some basic tests first and see if the idea works. This was found inside an actual power supply, so I'm assuming it should do the job because that's what it was doing before. A couple notes on the capacitors. They're recycled, the X type. Although this says 0.68, I'm actually only needing 0.48, but I measured these and their capacitance has actually dropped already. So together, I believe they give me the capacitance I need. I'll recheck these later just to show you as well. Okay, let's take all the parts out. And I just want to make sure that it lines up. Let me drill these holes and I will be back. Okay, the holes are done. Fit just nice, and this can screw down flat now. One thing I need to take into account are these little places here where the screws go in. Need to cater for this space when I place the components, because the components will be face down into the box. Next will be to solder those components, or just two first, the MOV and the thermistor. Okay, I believe that's the placement. Yeah, seems clear. All right. So the way this will work is that the AC terminal going into the isolation transformer, I'm going to disconnect it from the switch inside and connect it here. So I'm putting an MOV, don't really need it, but I'm putting one just as a precaution to help in case there's any surges, spikes, this will clamp them. And so this works by being an open circuit until there is a very high voltage at the input, then it will short circuit that incoming spike. And this here is like a 25 ohm, or is it more? Can't remember. Let's check it. Sorry for the glare. Okay. Okay, so that's 41 ohms. And the MOV is basically open circuit. Since they are recycled parts, I will check it as well. Yep, open. That's the one thing about using recycled parts. Okay. I will solder these two, and then I need to think about where to place the ins and out mains across these pads here. All right, soldering iron is on. All right. Next, I'm going to hook the basic wires up. Okay, I have the isolation transformer box opened up again. This is the switch. I need to remove this wire. Actually, this wire at the bottom. So what goes on here is that the brown and blue come in. The brown wire, if you can see it here, this comes out of this mesh of wires here, comes up into the switch at the bottom, then through the switch there's red now, turns to red, and that goes to the transformer. So I want to place my soft switch after the switch because I don't want it absorbing power when the unit is not being used. Only once I switch on the power, that's when I want it to be used. After here, where we have this line, instead of going straight to the transformer, I'm going to put it to this thermistor, right? Then the other side of that will come back into the switch and then go to the transformer. So I just want to test that to see if it stops the unit from tripping the fuse. Now, let's see if we can take this switch out first. I think these clips. Oh, okay, great. Yes, we've got a couple of screws at the front, which is what I need to undo to take out the wire. Because this wire actually goes to the transformer, I do not want to mingle with the wires attaching to the coil. I'm going to leave that as much as possible. So this wire, more than likely, I'll have to rearrange how this connects to my other wires. Okay, let me prep some wire that we can use. Quite solid. Okay. Okay, I've got the test set up. We have the switch here. The live wire comes through here, through this wire, comes through the switch, comes through this other brown wire which I've attached, goes through the thermistor, back out, then to the transformer. So technically that should work. I've tested, making sure that I haven't messed anything up. So wire, through. So it's quite straightforward. This thermistor, like I said, I got from a power supply. Based on basic internet specs and things, it should be sufficient for this application. So I'm going to switch this on and see what happens. I am expecting it to not trip the power. The power's off on this. Okay. All right, the transformer is on. I'm about to switch it on now. Let's see what happens. Just a note, sometimes it takes a few power cycles to trip the power. I don't know if that's because the transformer needs a bit of energizing, but let's see what happens. I have a thermal camera I thought I would use on this to see what sort of temperature we're seeing here. I don't know if I can show you effectively with the camera, but let's see. Okay, let's give it a shot again. You can see the temperature here. I'm recording the temperature on my phone. It's going to 60, 62, 63. These things can get to 100 degrees easily. Now there's not much current being drawn through this, I assume, because there's no load. It's just the transformer. But just with that you can see it's increasing. All right. So given that it takes a while to cool down, this is one of the reasons why it's also good to short out the thermistor so it can do power cycling quite quickly, one after another if you need to. What I like to do now is to actually remove the thermistor and just reconfirm this guy is going to trip for us. So let's do that and disconnect everything here so there's no power. Just going to put this here like that. I assume this wire is thick enough for the basics, but I'll just add 2 wires. Just to make sure there's not a surge of current that might melt my cables or something. Alright, so now it's shorted out, so technically this should trip. Okay, power's on, short circuited. Let's see what happens. Boom, proof of concept. You see, it stripped the power on the first try. So, this is awesome. It means I'm not wasting my time. We can do that one more time. Let me just switch on the power. Okay, here we go. Still shorted. Again. All right. So now I'm going to disconnect these wires. And let's see if it shorts now. Boom! No short. Fantastic. Power is on. Great. So this thermistor will do the job. I'll do it one more time. Beautiful. Okay, next step is to build up the board bit by bit and test it as we go. Fantastic. Okay, I just want to share with you as well, regarding this box, where do I put it? There's not much space inside here, like the wiring and whatnot. I could stick it to the top of the casing, but I don't necessarily want to drill holes in the casing to screw this to it. But I will if I have to. But there might be a possibility to stick it about here. Okay, so it's near the top. Oh, that may not work because this is the casing, right? And I prefer if I can somehow, if this is inside, have some screws go through these holes that already exist and screw it to the case from the inside rather than drill more holes. But because of these handles here, I can't put the box all the way in the center like I thought. So I'm going to be looking around to see how I could best fit this. And it may end up being that I do have to put it to the top. So you can see here the handles, and this is why I can't put this all the way to the top. I can't go to the edges because it gets in the way of the casing. So if I put it like this, that could work. Potentially I could put some Velcro in here. Maybe that's something to consider. So before I start assembling and doing that, I just want to highlight a couple of things. Okay, calculated I need about 0.487 microfarad capacitor as the dropping capacitor for the input of the circuit. Now these are X-type capacitors, and they're known to slowly lose their ability to keep their value. That means their value drops as surges go through these capacitors. Now this says 0.68, right? So over time, if this continues to degrade, I might need to replace them. So let's measure it. 0.68 is supposed to be. And we're getting 0.43. Yeah? Now I need 0.487. This is that. The other value, it's supposed to be 0.22. And it's 0.2, so not so bad. So I was going to put them in parallel, but my latest calculations require only 0.48. I do have another value. Okay, here is another one. This is 0.47, 0.35. So I need to find a combination It's going to do what I want. They're all X2 type. This is a 0.1, so it's like half the value. This is 0.05 microfarads. So I'm going to mix and match and see which one will get me closest to the 0.487. Alrighty, I found the combination. So the 0.481 plus this 0.051, or whatever that, together, they come to 0.489. And I wanted 0.487, so perfect. Using these two, match what I need. Hopefully they don't degrade too quickly. Okay, I've finished soldering up most of the wires, not all, mostly to the Zener output, which I want to see if that's working. So I've checked the wiring, looks okay, and so now I want to see if I'm getting the voltage coming out after these resistors, and then they go to the Zener, and I should see about 12 volts here. So that's what I'm going to do. Now initially I have this coming through a variac, so it's only set at about, I think, 20 volts AC at the moment, so this may not work yet until I juice it up a little bit more. So I'm just trying to take this step by step. All right, let's see, here we go. Okay, I've just hooked up the multimeter across the Zener, so I want to see how this voltage changes as I increase the AC. It's a bit hard to exactly know my variac voltage because it's not that accurate on the display. I need to measure the AC. So I'm just going to increase this slowly, probably at about 30 volts. Now I have AC on the meter. I'm just trying to see if there's much ripple. I have not connected the reservoir capacitor to minimize ripple yet. About 50 volts. Okay, I'm going to switch to just DC. All right, we have 11.5 volts already. That's good. So I'm going to keep increasing. At 80 volts. 90. Okay, 114 volts. So yeah, we're already at 12 volts, which is good. That seems to be working. I think I will also measure the voltage coming out of the diodes as well after the dropper capacitor. So let me switch off. Yep, 13.6. We're still only about 120 volts. If I keep increasing this, you see it goes to 14.5. I designed it to go to 15 volts. About 220 volts probably. I might just stop here. I haven't got an accurate measurement here. So yeah, 15 volts exactly is what I calculated from the capacitors before the Zener, which is great. Okay, let me switch that off. That's at 220, say. We'll measure across the Zener exactly and see what we have. Beautiful, 12 volts exactly. That's what we're looking at. Okay, this tells me the circuit is okay, which is great. I am, as a matter of curiosity, going to see if I can measure across these resistors. So 1.79 volts. That's at about 35 millivolts, and we're not really at 240 volts yet, I believe. Let's just double check. Yeah, we're only at 203. That's looking good. All right. Okay, I've done some updates to the board. The only thing left is to add in the wiring to switch the mains power. So I've added in the circuitry, and what we want to test now is to see if the relay switches after a second. I've had to change one of the resistors, the 100 ohm resistor here. It turns out one of them was bad. It was reading 100k instead of 100 ohms. So yeah, something went wrong with that. So I've replaced that with 220 ohm resistors. So together they make 52 ohms, which is cool. So that works now. So I'm going to reboot up the power and test the voltages again, make sure no wiring has gone wrong, and step-by-step test and see what happens. Power on, turning up the voltage, 76 volts. I'm going to just see what it says here. 81. All right, let me just check the voltage across this guy. 4.1 volts. All right, let's keep increasing this. 100 volts. 5.6. 144 volts. 7.5 volts. See what the voltage drop across these resistors is. 1.1. So that's about 21 milliamps, so we need more. Keep increasing this. All right, let's see what the AC is now. 220, 230. I would think that would be enough to give me the 12 volts now. 11.8. Okay. Now, I think the relay is probably enabled. So what I want to do is measure the voltage of the collector to ground. It should be 0. Yep. Okay. So I'm going to switch off and switch back on and see if we can hear the relay switch. Yep. It happens quite quickly. That's not 1 second. Okay, this is the voltage to the base. I don't think we're going to be able to read it. It's going to probably go too fast. Anyway, here we go. It jumps to 0.8, which is correct. I'm going to put the microphone close to the relay so you can hear it. Okay, here we go. Supposed to be a 1 second delay, but it's not. I'm going to make a couple other measurements across these resistors and see if we're getting the correct current flowing through them. .77 volts. So 1.77 divided by 52 gives us 34 milliamps. Okay, expected more. Let me check the Zener voltage, because I would expect this to be at 12 volts without a problem. So it's 11.8 volts, so it's a bit lower than I would have thought. Maybe because more current is being drawn than expected through the relay. I did calculate for 240, so let's take this to 240 volts. Alright, we're at 240. Switch this to DC. 11.8. Yeah, still not hitting the 12 that I want. Still enough to power the relay. Okay, so be it. I'm going to just measure voltage across these resistors for reference. 1.87 volts. Alright, that gives me 37 milliamps. I was expecting 50. So I believe the Zener may not be getting enough current, which is causing it not to have the regulation it needs, and maybe that could be causing the timing issues on the relay. Shouldn't, but it might. We'll look into that and come back to it. Okay, we are back. Made some changes. I changed this capacitor because the overall capacitance was a bit low last time. It was only reading 0.5 or so microfarads, and it's supposed to be up into 0.6. So I found I just put the wrong capacitor in, so I replaced that, and now we have this. If I measure capacitance, there, 0.634 microfarads now. So that should do the job. I also changed this resistor from a 5.2K to a 10K. So this together with a 200 microfarad capacitor, although it says 220 on the label, it's actually only 200. So together with the 200, it should give me 2 seconds delay before it switches on the relay. So let's power this up again slowly, checking everything as we go, and then do the final test. Okay, power on. Let's keep juicing this up. I think we're good. .240 volts. Let's see the voltage after the capacitor. 15.4 volts. Great, that's what it's supposed to be. And then let's look at the DC voltage at the Zener. 12 volts exactly. Love to see that. Okay, so that's good. The voltage drop across the resistor, yep, 11.2. So there's 0.8 across the transistor here, which would have switched on the relay. So now let's switch off the power and listen if the relay is switching after about 2 seconds. Here we go. No, the relay is switching straight away. Interesting. Okay, the Zener is getting the right voltage now. Things seem to be okay, except the relay is not waiting 2 seconds. I need to see what's going on there. Okay, we're back again. I have made a couple of changes. Basically, I've added in this extra Zener diode here. So what was going on before was that the voltage from the RC delay from this resistor and this capacitor, I had that tied straight to the base of this transistor. But of course, that would jump past the voltage necessary to switch on the base of the transistor, because we only need to get the base to 0.7 volts, and that would happen within milliseconds, right? So by adding in the Zener, what we're doing is to step up what comes out of the capacitor resistor time constant here. So once the Zener sees 7.1 volts at that junction, it will switch on, and then that will switch on the transistor. Now that 7 volts correlates to T equals R times C, which is about 2 seconds. So it takes about 2 seconds to get the 7 volts to switch on this Zener, to switch on this. So we have 0.7 volts from the transistor plus 6.8 volts from the Zener, and that generally should do the trick. So I'm going to ramp up the voltage again, and we're going to test and see how we go, just to make sure nothing's going funny. So variac on, power on, and ramping up slowly, about 50 volts, 60 volts, 75 volts. Just get it to 100 volts here. Let's see what we have on the meter coming out. This is live, so we have to be careful. It's 110 volts. We have 8 volts. Okay, good. DC is coming out. It's going to keep increasing this. 11.9. And we're seeing 6.7. All right, let me switch it off. All right, I'm hearing a delay of the relay switching on. Okay, listen carefully. And there we go. I'm going to put the microphone close so you can hear the relay. There you go. Let's take this up to 240. All right, we have 240 volts there. Let's switch it off. Yes. Now the RC time constant should be about 2 seconds or 1.8, 1.9 seconds. Not sure if it really is at that delay, but it's close enough. There's at least a second or so delay. There's some tolerance issues, of course, and some circuit influences, but it seems to do the trick. Cool. All I need to do now is wire this thermistor into the relay so that it gets bypassed when the power comes through here. Before I get into that though, I just need to figure out my wiring and how I'm going to install this into the box so that I can, ideally plug these wires in, or if I have to solder them onto the board, I will. But I'm just having a think about that. Okay, we are back with some updates. So I've added in this LED, which comes out of here and shows up here. And this is to provide an indication that the relay switch is still working. So I'm a little bit concerned over time, maybe these capacitors do further degrade, and over time their impedance increases, reducing the current flowing into the circuit and thus not allowing the relay to switch on. So with the LED on, it's hooked into the transistor, so when the transistor enables the relay, the LED will go on. I will be able to see this from the side of the isolation transformer by peering in through the vent holes, so at least once in a while I can check this to make sure everything is still okay, rather than worry that the relay is working or not, because if it doesn't work it will continue to function. It's just the thermistor here will get warm, quite hot I suppose. So that's just a little thing I thought I'd add on, a little light. So let's try it and see how we go. I'm monitoring the 12 volts across the Zener diode, so let's see how we go. Okay, switched on the power. Alright, now we're going to ramp it up and see what happens here. Okay, we are at 240. Alright, we have 11.9 0.17 volts. You see the LED is on here. Okay, so if we switch off and then we switch on, you'll see this come on a little bit later. There you go. Okay, that shows that the relay is working. So I'm going to do a couple voltage checks around to make sure everything else is okay. The current through the LED should only be 2 to 3 milliamps. It's quite low. I didn't want it sucking too much current. So let's see. It's this resistor here, and we have to be careful where we poke. So that's 10.2 volts, right? Yep, it's about 2.3 milliamps, which is good, not too much. The current that goes through the base of this transistor comes out to be about 400 microamps when you calculate the voltage across this resistor and the current that ends up going through that to the transistor, which adds up. I've measured that before. So everything else seems to be okay. I just want to measure the voltage, 2.12 volts across those resistors. So 2.12 volts, I think 50 ohms, we get 42 milliamps, which is just right. So 42 milliamps, and that is what powers the relay, which is about 33 milliamps, plus the current that's going through this Zener, which is also quite low. I'm going to put this together now and put it into the casing just to show you how that looks. Alright, this is the casing that I'm putting it in. I've attached a couple of connectors here so that I can easily dismantle this if I need to and take it off. I think I will put just some Velcro and attach it to the top of the lid of the isolation transformer box so I don't have to do any drilling. That should be strong enough to hold it in place. So for the moment, this will go in here. I've also drilled a little hole here to put the LED, so this will be mounted like this, and I'll be able to see the LED from the side. Because I changed to this capacitor, it's a bit taller, I need to have a couple standoffs here. So let's plug in this little clip here. I can just pull this off. This can go in here. Okay, it's a nice 3mm tight fit, which is good. This will come here like this. This cable itself for the LED is recycled from another board, which is great. I didn't have to do anything with that. Okay, so I'm going to put this bolt here to give it an extra few millimeters standing off, like that. This will come here. Let's put this through to there. Okay. Okay. You can see the wires all nicely come out this little hole here. Okay. Then the wires go into here. So this is the brown in that goes in here. So this is the one that connects to the fuse, so that goes straight in. Then it comes back out through this one. So this is the what I'm calling the out wire here. Okay, just tighten them up, don't want them coming out. Okay. And now the blue. Yep. These are just some cheap connectors I got at the local shop. They're not that great, but they do the job, I think. Alright, so that's done. Basically, that's it. I found a piece of laminate which I cut to size. I'm just going to stick that on with some, I don't want to drill it or screw it. There's nowhere really to screw this to. So I will just put some tape on here to hold it in place. And that's it. Nice, self-contained. I need to cover it because this is all live wires and I don't want it touching anything. So I just need to stick this laminate on and put some Velcro here and attach it to the box, and then wire up the isolation transformer wiring to this box like that. So it's self-contained, independent, and can be easily updated if we need to. Okay, let me stick this, bring up the transformer, and get the wiring done on that. Okay, welcome back. I'm now going to set up the wiring to connect to the box. So just to give you a review, this is the wire coming out of the switch, which will go into the switching box. This one, it will go into the in, and then the one that comes out from the box will go to this wire here. So essentially the live wire after the switch goes through the thermistor, which gets switched out, and then this becomes just a piece of wire which then bypasses the whole thing, so there's no resistance in the line. The thing is the box also needs the neutral wire, so I need to cut here the neutral wire and tap out of this the wire to plug into the box. Yeah, so that's something I need to do here, and I need to cut this and then join another blue wire essentially that allows me to extend from here up to the top. Because this comes in from the mains and then gets directly connected to the transformer, I don't want to mingle with there in terms of the transformer connection, so I'm just going to cut it here, just tap out, and that will be it. So just to highlight, I've joined this wire here already, I've soldered it, cleaned it up. I'm putting a special nylon type of cover over this to give it a little bit more robustness, and then on top of that I'm going to put the heat shrink to keep it in place. Same thing down here, I'll hook that up the same way. So right now I'm just going to open this up and prep the wires for that. So what I'll do is I'll take off these wire ties and tap out the blue wire, and that's about it. Okay, I'll leave that one there first. Just take this one out like that. Take this blue wire, I think we'll just snip it in the middle here so it's easy to get to. Now all I really need to do is skin some of this and connect the wire, but I need to cover it, right? So the only way to do that is with some heat shrink. Alright, that's cut. So I just need to connect it together like this, and hopefully that will work. So I'm going to put, hopefully there's enough space to do this. I'm going to put this heat shrink on. I don't want it to get hot and melt. And then we have this nylon stuff, which I got from an old toaster. Okay, just need to squish this a bit and hold it in place, and I'll do that. This clip, and then we are good to go. So I'm just going to tin this. Now the tricky part is to put these together. Put these together like this and have this one here. Maybe I should have wound them together. Alright, let's see what we can do here. It is a very tight fit. Okay, let's just check it. Yep, the solder's gone through both sides. Nice, good, strong solder join. Beautiful, beautiful, beautiful. Okay, that is great. Want to give this a bit of a clean. Not good to leave solder flux inside something for a long time. Okay, so this will go over the top of this. Hopefully it's going to fit. A bit of encouragement should do the trick, I think. Let me push this to the other side and then push this in. There we go. I was just worried, you know, with solder not being so flat, it might poke through the heat shrink. We really don't want that happening. So, just being extra cautious, putting this extra stronger insulation over the wire, and then I will put this over the top to keep it in place like that. All right, I'll put the heater on that later and shrink it up along with this one, and then it's a matter of hooking these wires up to the switch box. So let me get that sorted out. Okay, so now that these are hooked up with the extra insulation here and here, as you can see, right, I'm going to heat shrink this over the top just to keep it in place. So there, and this one as well, about there. So this is my little heat gun. It gets hot pretty quick, so I'll do what I can so it doesn't overheat things. Don't leave it there too long and melt the wire, that's good enough. And the one down here, to be careful with this one, are the wires here. Now that they're all done, we just need to plug it all together. Okay, so once again, summarize, the blue wire is coming through here as per normal. It's been tapped out of here. The brown wire comes from here, it goes up through the switch, comes outside the switch. Once the switch is set to on, this becomes live, it goes through our little box, and then the box comes out through this one and goes to the transformer. Now I've made these wires extra long, as you can see here, and I'll demonstrate a bit later, but they had to be long enough so that when I take off the lid of the box, these cables can go high enough so that I can flip it over and deal with what I've got to deal with. What I am going to try to do is see if I can put some cable ties and tidy these up a little bit, but let's see one step at a time. So I'm going to put some cable ties back in here. So we have a little box here. This is the in on the brown. I'm actually using painter's tape to hold this on because it doesn't get sticky. So that's the main reason I'm using it versus electrician tape. And it should be fine sitting in there by itself. Now for this one here, this is the one that comes out. Okay, also nice and tight. All right, they're all good. Now the blue wire. So the blue wire bit. I've done this in the way that when this goes up, you see the wires, the path of the wires is sort of taken into consideration. And done. It is wired. And this will go here. Alright, let me put this on the box, lid I should say, and see what that looks like. Hopefully I can show you what I'm trying to do. So this box gets stuck to these 3M strips, so I can just clip in once you align them properly. There, sort of clicks in. That's stuck in now. These cables here, I want them to sort of come together. Sorry if this is going out of focus, but these wires, maybe we can sort of put a little wire tie to hold them in place here. Let's give that a try. Not sure how good it will be, but let's see. Now I'm not going to make it tight, just loose like this, just enough so that the wires can stay in place there. Okay, I'll just leave that for now. So the plan is I can easily put this on just like that. Now, I know you can't see much, but that's it. So when I want to take this off, there's plenty of cable to come off like this and deal with anything that might have gone wrong. Okay, so yeah, before I screw it up, I think it'd be good to test it. Okay, let's switch on the power and see what happens. I haven't not actually tried this before or connected up, so I'm hoping it all works. Okay, the power seems to come through. Let's try that again. Yes, I'm hearing the relay switch. The little LED is on, which is great. I'm not sure if you can see it. That's the only thing. Let's switch it off again. Don't really have anything reflective, but let's see if you can see the LED come on from the ruler reflection. Okay, here we go. Ah, there you go, you can see it in the camera there. She works. No tripping. Fantastic. Wow, all this work and effort to put this little box together has paid off. So now I can finally get to use this isolation transformer for my projects and move things a lot faster moving forward. I'm very happy about this. Awesome. This is what I'm talking about. Very cool. Got to celebrate the small victories. I wanted to highlight, this isolation transformer is actually not bad. It has a good screen display of what's going on. They have a control board here which actually switches in the output voltage, right? The voltage that goes out. There's a relay on that board which switches the power to go out after a delay. So they have catered in case maybe if the load is drawing a lot of current and you just power it on and the output has a surge and it trips maybe. But they didn't consider the input rush that may happen from the input side. So this solution addresses that problem. So now we have an input and an output surge protection for this product. Thank you so much for sticking with me on this project journey. I really appreciate you watching. I hope you got something from this. What I got is I learned about this capacitor dropper circuits and how widely they are used across different products in consumer electronics. So I've applied it here. Hopefully somebody can use this for yourself. Just be warned, it's a dangerous circuit to implement and you need to take the necessary precautions. And if you have not done this sort of thing before, or you have not dealt with high voltages before, best don't do it, because slip of the hand and you're cooked. So please like and subscribe. Can't wait to catch you for the next video. And thanks again. Take care.